viewers, welcome to CEC lectures. Myself Dr. Preeti Jagmani from Department of Computer Science, Aryabat College, University of Delhi. In this series of our operating system concepts, presently we are learning process synchronization, and in the previous lectures we have seen two classical problem of synchronization, which are the producer consumer problem and the readers writer problem. And with this agenda in our mind, today's situation is, or today's problem which we are going to discuss in this lecture is the third classical problem of synchronization, which is known as dining philosopher's problem. So let us begin with this. Let us try to understand first that what is this dining philosopher problem is. Dining philosopher problem, we can say it's an kind of example of a large class of concurrency control problem. It is basically a simple representation where we have kind of several processes and several resources are also available, but we need to allocate those resources to these several processes in a deadlock free as well as in a starvation free manner. So we have we actually don't want the situation of the deadlock, and we don't want that any process should go into the starvation. So in order to establish a deadlock free and a starvation free situation, we need to see how these various resources can be allocated to several processes. So this dining philosopher problem is a classical example of these large class of concurrency control problems. So with this, what is actually this dining philosopher problem? Let's say we have five philosophers who are spending their lives thinking and eating. These philosophers share a circular table which is surrounded by five chairs, and these five philosophers are sitting onto those chairs. In the center of the table, we have a bowl of rice, and the table is laid with five single chopsticks. Now here these chopsticks are representing the resources, while these philosophers are we can say representing the processes who are looking for these chopsticks. Now from time to time a philosopher is getting hungry and tries to pick up the two chopsticks that are closest to her. That means the chopsticks that are between her and her left are at the right neighbor. So the two chopsticks, one from the left side and another one from the right side, the philosopher is trying to pick up whenever the philosopher is getting hungry, and then the philosopher is going to eat some rice. So that's what the problem is. So philosopher here are the processes which are looking for resources, and these resources are nothing but chopsticks. Now here let us try to understand that there are five single chopsticks and five philosophers are sitting, and in order to kind of understand this scenario, we can have a look on these figures. We have five chairs around a circular dining table. A bowl of rice is kept in between, and we have five chopsticks. So even if one process is, or one philosopher is trying to eat some rice, she will be picking up two chopsticks, one from the left side and another one from the right side. So what are the stages a philosopher may go through? A philosopher may pick up only one chopstick at a time. Obviously she cannot pick up a chopsticks that is already being taken up by a neighbor of hers. So she cannot pick up a chopstick that is already in the hand of a neighbor. When a hungry philosopher has both her chopsticks at the same time simultaneously, she eats without releasing the chopstick. When she is finished with eating, she puts down both the chopsticks and starts thinking again. So what are the stages when in which the philosopher can be in? So one stage is she is thinking, so no need of resources that time, resources as in chopstick. One situation is she is getting hungry, so she will try to acquire the resources, and the third one is she has acquired the resources, she has acquired two chopsticks, and now she has started eating. So now the two chopsticks or the two resources are with that particular process or with that particular philosopher. So, what is the solution to represent each chopsticks, or what is the solution to this particular problem? We can say, can we represent each chopstick with a semaphore? Yes, we can. So, a philosopher tries to grab a chopstick by executing a weight operation on that semaphore, and then she is going to release her chopstick by executing the signal operation on the appropriate semaphore. So, basically what are we trying to say here is, we have a semaphore which is, let us say, named as chopsticks, and we have 5 such semaphore, and all the elements of this variable semaphore, of the type of the variable semaphore, the variable chopsticks, are initialized to 0. So, whenever a philosopher is hungry, she will tries to grab a chopstick by executing a weight operation on that semaphore, and it is going to release her chopsticks by executing the signal operation on the appropriate semaphore. So, 5 pieces of shared data in the form of semaphores, where each one is initialized to 1. That could be kind of one way to a solution. So, using this, if we need to kind of code this solutions, we have a do while loop as we do in all other problems. So, our philosopher who is trying to grab the resources will be grabbing 2 resources. One is a chopstick, let us say I, if I am talking about the ith philosopher, and another chopstick which is I plus 1 mod 5, because there are 5 philosophers sitting on a circular table. So, if I am talking about the first philosopher as 0, so it is going to take, or she is going to take chopstick 0 and then chopstick 1, which is 0 plus 1 mod 5. So, the chopstick, 0th chopstick and the first chopstick it is going to take. Or maybe if I am talking about, let us say kind of third philosopher, so chopstick 3 and chopstick 4 will be taken by the third philosopher if I is equals to 3. Now, after grabbing 2 chopsticks or 2 resources from her left and right, philosopher is going to eat for a while, that is obvious, and then these chopsticks, which are chopsticks I and chopsticks I plus 1 mod 5, are going to be released with the help of a signal function call, and then the philosopher is again in the state of a thinking state of thinking, or it is thinking, it is she is in thinking process, and this will go on. One who is looking for that particular resource, or the philosopher who is looking for that chopstick, will grab 2 chopsticks, wait will be executed on those 2 semaphores, that means they are logged in a way, then it is they are going to eat for a while, and then will be released with the help of a signal function call. Seems fine, but this solution is having a problem in the situation that no 2 neighbors are eating simultaneously. So, for example, let us consider the philosopher number 0 and philosopher number 1. So, if philosopher number 0 is eating, she is taking chopstick 0 and chopstick 1. So, obviously, the philosopher 1 will not take the chopstick 1, which is maybe on his left side, on her left side. So, no 2 neighbors will be eating simultaneously, but the main problem with this solution is this solution must be rejected because it could create a deadlock. Now, how it is going to create a deadlock? Let us try to understand. Suppose that all the 5 philosophers become hungry at the same time, and each one of them is going to grab her left chopstick. Now, what will happen after this? All are hungry, no one is eating and no one is thinking, and each one of them is having one chopstick in their hand, also each one of them is looking for the second chopstick which is not available to them, and each one is waiting for the other to drop the chopstick, or to, you can say, put down the chopstick or release the chopstick. And all the elements of chopsticks, because they are busy, will now be equals to 0, because earlier we have set them 1, and now the chopstick has been taken by the philosopher, so it will be kind of programmed as that chopstick is now equals to 0. So when each philosopher tries to grab her right chopstick in this situation, she will be delayed forever, because right chopstick is anyways not available, and each one of them is looking to the another one for the release of their chopstick. So basically this is going to create a situation of the deadlock. So what could be the possible situations, possible solutions? So can we say that one possible solution is we can with 5 chopsticks we can allow at most 4 philosophers to be sitting simultaneously at the table. So not the 5 but only 4 philosophers are sitting at the table and they will be using the resources. Also with this constraint, a philosopher is allowed to pick her chopstick only if both of the chopsticks, that means one which is available on the left and another one which is available on the right, are available. No one is going to hold only one chopstick. So we will be allowing a philosopher to pick up her chopstick only if both the chopsticks are available. That means in order to implement this situation, we must say that she is going to pick the chopsticks in a critical section, because then only it is possible. Another solution which is we can say is an asymmetric solution is an odd number philosopher picks up first her left chopstick and then her right chopstick if available, whereas an even number philosopher picks her right chopstick and then her left chopstick. So this is kind of an we can say asymmetric solution, because this is not symmetric to all the processes. Depending upon the number of the process, whether it is an odd number or it is an even number, this is going to kind of change the strategy. So as we have seen earlier that if we are looking for a solution to any classical problem of synchronization, we are looking such a solution that is that is going to protect the system against the deadlock. Not only the deadlock, but the process must guard against the possibility of the starvation. So basically what I am trying to say here is any satisfactory solution to the dining philosopher problem must guard against the possibility that one of the philosopher will starve to the death. And these two are kind of we can say very different situations. That means a deadlock free solution does not necessarily eliminate the possibility of the starvation. So we have two conditions, or we have two requirements which we are we can say looking from the solution, or which we have two expectations from any solution which we are going to approve. That is, it should land up in a deadlock free solution or deadlock free situation, and also it eliminates the possibility of the starvation. And now what are we going to use here as a solution is the construct which is monitor. Now let me explain what is monitor, but before going into explanation of monitor, let us try to try to have a quick recap that what we have done in this lecture. So we have started with dining philosopher problem, and we have explained what is dining philosopher problem, which is the scenario of a dining table having n resources and n processes, but each process is in a need of more than one resource, and the situations could be processes are not looking for the resource, that means the philosophers are thinking, or they are looking for the resource, that means they are hungry and they are eating, that means they have grabbed the resources and they are into the critical section and doing some critical work on those in which cannot be shared. So, what could be the solution of these things? Either we can have some asymmetric solution which is going to be have a different strategy for odd numbered philosophers or odd numbers processes, or we may have an even number process, then the situation is going to be different. So, that could be one of the solutions. Another solution is we can allow at most 4 philosophers to be sitting simultaneously. Now, any of the solution which we are going to kind of approve, or which we are going to take up, that should lead to a deadlock free and a starvation free solution. So, here the solution which we are taking up is named as monitor. So, now what is this monitor? Basically, this monitor is an abstract data type, and I hope you understand what is abstract data type. I'm going to elaborate this in a minute. So, this abstract data type is a data type on which the variables, that is the data, as well as the operations which can be taken up on those values or on those variables, both are defined along with the bodies of the function that operate on those variables. So, an abstract data type is a data type that is going to declare the variables whose value defines the state of the instance, and not only the variables and the values, but the bodies of the function that operate on those variables. That means the functions which are going to take place on those variables will be defined. So, this is what abstract data type is, and we have already you must have already you are aware of, I am sure that you are aware of this abstract data type. So, monitor is also an abstract data type. This is going to include a set of programmer defined operations that are provided with mutual exclusion within the monitor. So, here we have a monitor, the situation here is of a mutual exclusion, and this monitor being an abstract data type, this defines the operations that are provided with mutual exclusion. And so, one thing here, after understanding this monitor, we need to be very clear that the representation of a monitor type cannot be used directly by various processes. That means a function defined within the monitor can access only those variables which are declared locally within the monitor and its formal parameters. Similarly, the local variables of a monitors can be accessed by only the local functions. So, that is a constraint kind of we can say, as we are implementing this monitor as an abstract data type. So, here I am repeating again that representation of a monitor type cannot be used directly by the various processes. So, monitor being an abstract data type, in this situation, this monitor construct is going to ensure that only one process at a time is active within the monitor. Consequently, the programmer does not need to code this synchronization constraint explicitly, we can say, because this is already implicitly kind of coded, we know this. But if we talk about our dining philosopher problem and the concept of solution, concept of monitor as a solution to this dining philosopher problem, we need to see that how this monitor is going, how are this abstract data type which are named as monitors are to be used for the solution of this dining philosopher problem. So, here we need to illustrate that a monitor, when taken up as a solution to the dining philosopher problem, this is going to present a deadlock free solution to our problem which we are considering, which is none other than dining philosopher problem. So, monitor concept is presenting a deadlock free solution to the dining philosopher problem. And what is the solution? The solution imposes the restriction. The solution comes here with a restriction, and the restriction is that a philosopher may pick up her chopstick only if both of them are available. A philosopher cannot pick a chopstick if only one is available. That means it is not allowed to hold on the resources unnecessarily if both of them are not available. Then in that situation the philosopher will not be allowed to pick up the chopsticks, and this is going to give us a deadlock free solution. Now, in order to code this solution, we need to distinguish among the three states in which we may find a philosopher. And what are these three states? I have already told you earlier that these three states are the philosopher is thinking, so that means no resources are required or no such critical resources are required. Then the philosopher is hungry, that is the second stage, that means the philosopher is looking for some chopstick or looking for some resources. And the third one is the philosopher is in a eating state, that means it has taken the hold of the resources and it is also using the resources. So, in order to distinguish among these three states and in order to have this implementation with the monitors, we can have these three states as thinking, hungry and eating in the form of an enumerated variable, which is a common or which is a situation as we code in enum, thinking, hungry, eating. So, these three states, these three variables, and we have taken this is in an array of state for, as we have 5 philosophers in our problem, the array is of 5 numbers. So, the distribution of the chopsticks is being controlled by the monitor in when we talk about this dining philosopher problem, and the solution says that each philosopher before starting to eat must invoke the operation of pickup. So, that means the pickup operation says it is going to pick up the chopstick, and I have cleared it in the earlier kind of some moments earlier that philosopher is going to take the resources only if both of the resources are available, that means both of the chopsticks are available to her, then only it is going to pick up. So, whenever this philosopher is taking the action of pickup or it is invoking the operation of pickup, that means it is having the kind of 2 chopsticks available, one on the left side and another one on the right side. And then when the philosopher has picked up the both chopsticks, then this is going to be carried over in the process of eating. That means the this act may result in the suspension of the philosopher process. And after the successful completion of the operation, the philosopher may eat. So, it has picked up and it is going to eat. So, picked up not only 1 but picked up 2. So, following this, the philosopher invokes the put down operation when she is done with the eating process. So, that means the philosopher I or any philosopher must invoke the operations pick up and put down in a particular sequence, and the sequence is about the pickup is the first, then it is going to be in the eat scenario, that means pick up and then eat, and then we have put down, and the sequence is actually shown on the screen. So, we have dining philosophers dot pick up I, that means it is picking up the resource, and after picking up the resource it is kind of in the process of, we can say, eating. And then we have after finishing of the eating, it is going to say dining philosophers dot put down I, that means whatever resources have been taken up by the dining philosopher, now those resources have been kind of released. Now, this solution ensures that no 2 neighbors are eating simultaneously and no deadlocks will occur, because this is kind of a solution which says that it is dining philosopher is going to pick up something, then in the eat, and then in the put down situation they are. So, no 2 philosophers which are sitting which are neighbors to each other can be eating simultaneously, because 2 chopsticks are required. deadlocks will not occur because there is an kind of a specific sequence of the implementation of this pick up and put down process. However, the solution which we were looking for earlier was we tried for a solution which is deadlock free, also the solution which is kind of free from starvation. But the solution which we have given till this point is ensuring that no two neighbors are eating simultaneously and no deadlocks will occur. However, it is possible for a philosopher, at least in this situation or with this solution, to starve to death. So, it is a possibility that starvation situation may occur with this solution. So, further we will be taking up these solutions in our upcoming lectures. Now, let me recap this lecture. What we have seen here is we have started with dining philosopher problem, then we have seen what is the construct of monitor which is going to give us the solution to this dining philosopher problem, and we have presented one solutions which is not the starvation free, but yes, it is ensuring that deadlocks are not going to occur here, and that solution has been kind of implemented with the help of monitors. And here is a list of references which is being used for the preparation of lecture. Hope you had a fruitful learning. Thank you.